Welcome. My name's Margaret Swerdloff, and I'm an R&D Engineer at BrainRobotics. Today I'm going to walk you through the design of microprocessor knees and how the real-world mobility outcomes of patients who use Neuro, the microprocessor knee shown here on the screen. My goal for this talk is to connect the technical decisions in the design of Neuro to the outcomes we're seeing in the field and the research we're driving towards. We'll start by asking how the features of the MPK can specifically address clinical problems across the mobility spectrum. From there, we'll hear about how users are experiencing the knee in the real world. And finally, we'll close out by laying out how we're turning those insights into evidence-based research. Let's start by looking at how specific features in MPKs match or map to specific clinical needs. For Neuro, this design wasn't driven by just what can we do, but what patients actually need. Individuals with limb loss or limb difference can be described using a clinical scale from K1 to K4, based on their functional mobility potential. K4 users are high-activity individuals such as athletes. K2 users on the other end of the spectrum have mobility potential, but need significantly more support. K3 users are those who fall somewhere in between. Most MPK research has focused on the K3 and K4 end of the spectrum. However, K2 users show potential to benefit from these technologies and are still typically underserved. MPKs, however, such as the Neuro, can serve all three levels, and that goal is what motivates the designs and features for those that we'll talk about today. So far, we've covered who we're designing for and next we'll go into how the knee will move. And then finally, how it knows what to do in real time. The gait cycle describes what happens during a single step, and it has two distinct phases. Stance phase is when the foot is on the ground. The knee needs to provide higher resistance to bear the weight of the user. Swing phase is when the foot is in the air, and the knee needs to move freely with low resistance to bring the leg forward. A microprocessor knee has to distinguish between these phases in real time and adjust its resistance accordingly. Now, getting that wrong has severe consequences for safety and energy expenditure. So how does the knee actually know where it is in the gait cycle? That's the role of the IMU, or the inertial measurement unit. It's a small embedded sensor in the knee that continuously measures acceleration, rotation, and orientation. In the Neuro, the IMU feeds a constant stream of positional data that drives the knee decisions. It's the sensory foundation of everything that the knee does. Now that we have that context, let's look at how some features in Neuro map to specific clinical challenges. Real-world walking is unpredictable. There may be uneven pavement, unexpected curbs, and distractions. Neuro was designed to allow the user to return to stable position by detecting when the gait pattern has been disrupted, and increases the resistance to prevent a fall. This is relevant across all K levels, all mobility levels, but is especially meaningful for those who have less compensatory strength to recover on their own. For higher mobility users, the design challenge shifts from stability to adaptability. The walk-to-run feature, for example, enables smooth cadence transitions so that a user moving from a slow walk to a faster walk or even a run can be confident that the knee will keep up with them as they increase their speed. Custom modes allow users to define specific settings for activities outside of their standard walking, such as cycling, golf, or working out. This is important because these users are pushing into activities that standard gait assumptions weren't built for. Other features have been designed specifically to tackle clinical challenges of K2 or lower mobility users, such as the yielding limiter. This reduces uncontrolled flexion during stance, making standing and walking feel more stable. Together, these features are what make neuro viable across the full mobility spectrum. That's how the design maps to the clinical need. Now let's look at what we're actually hearing from the people using it. This is where we shift from the design intention to lived experiences. We're not going to present clinical findings here, but we have early anecdotes from a small group of users, and their stories are meaningful because they're telling us where to look in our research. So like I said, we have a limited cohort of ambassadors who are early adopters, and they've been sharing their experiences with us and participate in quarterly interviews with our field team. The goal of these interviews is to help us understand what happens when people do the unexpected, and not just in one type of patient population, but across diverse demographics. 3 themes have emerged consistently from these interviews: decreased fatigue during daily activity, reduced compensatory patterns, and an increase in the variety and intensity or potential to do more of the activities that they want to do. Hearing these themes across independent users is what's motivating our formal research agenda that I'll go through next. Our final question is, how do we build an evidence base that clinicians, payers, and patients can actually act on? Our research roadmap was organized across 3 parallel tracks, each capturing a different layer of what improved mobility means. These 3 tracks are designed to complement each other. Track 1 captures how patients perform on standard clinical outcome measures. Track 2 captures what we can measure objectively in the lab. And track 3 captures what the device itself records over time. No single track tells the whole story, but together we get a comprehensive picture. So I'll walk you through each one. The first track is built around standard outcome measures collected at multiple patient clinics. These are validated tools that the broader clinical community already uses and can trust, which matters for how our findings will be received and acted on. Data is collected at intake and updated quarterly, so we're building a longitudinal picture of how patients progress over time. This track keeps patient outcomes at the center of our research. The second track moves into the lab, where we can measure things that patients may not consciously notice, but have long-term implications. Biomechanics analysis lets us quantify movement quality, such as gait symmetry, compensation patterns, and joint loading. Metabolics testing helps us measure the energy cost of walking, which is a proxy for fatigue. And we're exploring parameter optimization to systematically identify the ideal settings for individual patients. That feeds both into clinical and our broader understanding of what makes the device work well for different users. The third and final track uses the knee itself as a research instrument. Because neuro continuously captures IMU data, parameter settings, and usage statistics, we have the potential for longitudinal data at a population level, the kind of patterns that no lab study can capture on its own. But this only works if patients trust the system, if they're willing to give us their data. So we've treated data privacy as a design principle. Understanding what patients are comfortable sharing and being transparent about how that data is used is foundational to maintaining the trust of people that this research is ultimately for. To close, I want to briefly summarize this talk. We discussed the features that were designed to address clinical problems across the mobility spectrum. We're hearing early anecdotes from users that suggest improvements in fatigue and activity. And we have a research agenda designed to validate those voices with evidence that leads to better outcomes for patients. Thank you to all our collaborators at LimLab, Texas Christian University, and Texas Robotics, of course. Happy to take any questions on any part of this talk. Thank you.
Thank you very much for that presentation. To be clear, you're actually integrating microcontrollers that have sensors and actuators to respond to the environment. I'm curious about what kinds of algorithms or processing. Is that the fundamental development for BrainRobotics, is to develop those algorithms that work within these prosthetic applications?
Yeah.
Provide a little more guidance there.
Yeah. So what I'm hearing is you're curious about the overall goal of our algorithms, right? And so we are a prosthetics manufacturer, and whatever algorithms work for patients is what we want to do. So we're looking at, yes, very advanced microprocessor control algorithms, and maybe some less advanced ones if they're more stable and more reliable for the patients. So our knee, we have a microprocessor knee on the market. It's available for patients to get from their clinician, and it uses a closed loop controller that I don't know how much detail I can go into about how it functions, but basically it looks at the sensor data and decides where the knee is and how it should respond. Does that answer your question? Okay. Yeah.
Hello. Yeah, I just had a question about what you were just referring to, I guess, as concerns control. And I don't know how much detail you can go into this, but you did mention symmetry. So I'm wondering if you have just some sort of, I guess, like constraint propagation algorithm that's in place that can measure, like, when a movement is, I guess a movement of the limb, of the artificial prosthetic limb, is outside of some parameter, maybe thinking of a manifold, like outside of some manifold, and collapsing it back to the manifold. Is that too detailed as far as?
No, that's not too detailed of a question, but I kind of want to bring it back, bird's eye view. So these systems need to adapt in real time, and they need to be housed in an embedded controller. So I would say using the word manifold is probably more complex than our product actually works right now. That's not to say that we won't have one in the future, but to answer your question more generally, when someone is outside of what the expected gait looks like, then yes, it will bring that patient back to a stable positioning, or allow them to bear weight on the knee. And that is what we have referred to as our stumble recovery feature. Yeah.
That's all the time we have for questions. Thank you so much. Let's give Maggie another round of applause.